Hello, everybody. Welcome to our Gamma seminar. Today we have the pleasure to guest Małgorzata Flis, who is a student of the University of Warsaw. And today she's going to talk about a Lie groupoid and algebra approach to ordinary differential equations. So this is something like a review with a few new results. Let's just a little bit. And it's a work in progress, yeah? So Małgorzata, please go ahead. The floor is yours.
Thank you for the introduction. So yes, this is a talk which I've done with collaboration with Professor Javier de Lucas, and this is on Lie groupoid and algebraic approach to ordinary differential equations. So first start, let me give you a quick outline of the presentation. So I want to have a little motivation behind the topic of the presentation. Rather than introduce, probably just review the basic notions, which would be pseudogroups of diffeomorphisms and Lie groupoids, and then a brief, like a connection, like a bridge between them. Then Lie algebroids as their own, and also Lie algebroids of Lie groupoids. I will give you an example of a Riccati equation and briefly state some further possible directions. So, when we are discussing different types of symmetry analysis framework, we also encounter the task to integrate the vector fields. So if they're not globally defined in general, they should not be, sometimes they are, but in a classical setting, what they are then integrated into are pseudogroups of local diffeomorphisms. And another approach that can be taken is a theory of Lie groupoids and algebroids. So those two frameworks coincide in something called germs, but first, let me just start that I will give you the idea of those notions, the connection between them, then move on to Lie algebroids, and then illustrate this with an example, which is a Riccati equation, but those could be applied to many systems physically also relevant. So like Lie point symmetry analysis, time-dependent systems, and so on. So let me start with pseudogroup of diffeomorphisms. So
Małgorzata, if
yes.
you let me to just comment a couple of things, because in one physical motivations for this is that when we have systems of partial differential equations and we look for least symmetries of the differential equations, these least symmetries, they span a Lie algebra, but normally in many cases a finite dimensional one. But when we try to integrate to a Lie group, it's not a Lie group, yeah? So in general, but in many cases we can describe it, or what we pretend is to do it with a Lie groupoid, yeah? And a Lie algebroid associated to it. And the cool thing is that many technical things that they are done locally, normally in physics, they can be avoided. We can use this approach. And for example, things like reduction of Lie groupoids or simulated Lie groupoids and things like that naturally appears in everyday problems. Yeah, so it's the thing that when we have these partial differential equations, there are problems where there is no integration of a Lie algebra straightforwardly to a Lie group because the vector fields normally they are not complete. And so this approach, this gives an introduction, nice introduction of a complex, a modern differential geometric technique to study standard problems. Yeah, many problems in a very precise manner. So this is more or less how I say it. Thank you.
Yeah. Thank you very much for this remark. You really said how it works, because really it might seem like a little intimidating to introduce those notions, and many people that I've discussed with were like, "Oh, why you even need those Lie groupoids, not just Lie groups?" But actually, this is very much relevant and prolific in physical theories. So. Let me start with a definition. So having a manifold M as the group of diffeomorphism on that smooth manifold is a family of maps on open subsets of this manifold that satisfied some basic axioms, and those axioms would be that there is an identity map between any open subset of this manifold. Elements of a restricted domains are also in this family, so this is the family of maps with restrictions. Compositions are included if the domains are well defined for the composition, and for each map in the family we also have included an inverse that also belongs to the family. To connect it with the theory of integrating not the theory but just integrating the vector fields, we want to say what is an object that is generated by the vector field rather than this one parameter group of diffeomorphisms, which when the vector field is complete, and that would be the pseudogroup generated by the flow of the vector field, which is the smallest family, the smallest pseudogroup, containing all the local flow maps and their restrictions, which is denoted by this in this notation like that. Okay.
Sorry, Małgorzata, just one comment.
Okay.
The notion, the term complete vector field is quite standard in the literature. It's very standard. But incomplete vector field, as much as I know, does not. Okay, yes, it's just a comment that is something that does not appear many occasions. In any case, it's something you can understand, but it's not a formal notion. Okay.
Yeah, thank you very much for this remark. Okay, so I will give you an example of a pseudogroup of diffeomorphisms that would be relevant later in the example that I will consider of the Riccati equation. So having a vector field on the real line, which is x squared, we can integrate it into the local, not globally defined flow of this form, and for some parameter t, so maybe let's call it time, for time t, the domain of the flow is without this 1 over t element of the manifold. And the pseudogroup of diffeomorphisms which is of that sort, satisfy all the group actions. So if we want to consider the identity maps, we basically do it at the unity. So at the 0 value of the parameter, all of those are diffeomorphisms and are present in this family. Then if we restrict those diffeomorphisms, they are also diffeomorphism present in the family. We can compose them when the composition of the flows is well defined, and then such a domain is an open subset of the domain of the flow which is within the composition. And since this domain is an open subset, it's also in this family, and the inverse naturally is also present. So other than this vector field, rather than being a generator of the flow, which give rise to a one parameter group of diffeomorphisms, this flow gives rise to a pseudogroup of diffeomorphisms. Right.
Just one question, Małgorzata. Have you worked out what VT is exactly?
What once again DT?
BT, yeah. You say that phi xt is a local flow, yeah, is one of these diffeomorphisms, yeah, local diffeomorphisms.
Yes.
And the domain is UT, and the image, yeah, anti-image is VT. So what does it VT is?
VT, if we exactly.
Yeah. I mean, could you say that it is some particular subset, or you don't know?
Right now, I don't know, but in general, the maps of that form are part of the Mobius transformation. Maybe that has something to do with.
Yeah, okay, but well, you could try to obtain the image for every x, yeah, because you say that down if you have t equal to 0, yeah, you can see that it's an identity, yeah. for instance, t equal to 0. Indeed, the ut, well, okay, anyhow, you could check, you could work out this a little bit more carefully, certain things, but it's okay, Thank you.
Okay, I will work that out. Right. So with that, I would now like to move on to the Lie groupoids notion. So it will again be just a review of something I think you all know. So groupoid would be a category in which we have those two sets, so the set of arrows, set of objects, and the structure is given by the following maps. So we have the source and target, that to each arrow assign the source element and the target element, the multiplication, which is the composition of any two arrows, but in the composable arrows set. So the target and the source of two composed arrows must coincide, and the unit map assigns to each point of the set of objects the unity, so an arrow that starts and ends trivially in that same point. And we have also an inverse map that inverts the arrow from the target and the source are inverted. So if we want to speak about the Lie groupoid, it's just a groupoid in which G and M are smooth manifolds, source and target are submersions, and other structure maps are smooth maps between those manifolds. And the axioms that have to be additionally satisfied by those structure maps is the associativity of the multiplication. So the property that the source of the composition and the target of the compositions are appropriately one or the other of the arrows, depending on the order of the composition, if they're composable. Then the unity have the axiom that composing it with any arrow gives any arrow, but also the order of composition matters. Then the source and target of the unity are just the element in which the unity is taken. For each element, we have an inverse, and those are, again, identity arrows appropriately with respect to the order of this composition. And with the inverse element, the source and target are like inverted. So the source of the inverse is the target of the element, and reversely the same. And this is just an illustration, a very, very basic picture of composable arrows. So we can invert them and then also compose the inverse, but in an appropriate order. Yes. So I would give two examples of Lie groupoids. I think you are also familiar with them, but will be relevant later with the example. So if we consider an arbitrary action of a Lie group on a manifold, then we have its image that looks like that. And we can actually define an action Lie groupoid, which with the manifold of arrows being the domain of the action, and the manifold of objects being the manifold that the Lie group is acting on. And the structure is as follows: the source are just the objects, target are the images. Then multiplication is possible only if the action can be taken in that point. So the domain is also relevant here. The unity is the action with the arrow with respect to the identity element of the group, and the inverse we have to consider the action with a inverse element on the actually acted on with G previously on X. And we have coinciding isotropy groups and orbits with the action of the Lie group. So this is in case of a action of some Lie group. We can think of another example of a Lie groupoid that would be a flow Lie groupoid. So having some vector field on a manifold, we consider the flow with one-to-one correspondence to a vector field that is locally defined on some domain. And this domain would actually turn out to be the manifold of arrows of the flow Lie groupoid, with again the space of objects being just the manifold. And the structure is very similar to the action Lie groupoid, except now not the images of the action, but rather the images of the flow would be the target, and acting the unity would be acting with a flow with the parameter t equal to 0. And the inverse would be taken at some element but with minus parameter t. Multiplication will coincide here with the composition of the flow. So the arrow of composed elements would be actually the same as an arrow with the source at the same point, but then the parameters added up together, but also defined on the set of composable hours. And then the orbits coincide with the directly with the images of integral curves of this vector field. And isotropic groups are as follows. So I have just a very basic illustration, the same as for the general Lie groupoid, but here you can see that we're going along the flow maps. Okay, and now when I have introduced the notion of pseudogroups of diffeomorphisms and Lie groupoids, I would like to actually show or again just revise to you what is the connection between those two, because I think this is also very interesting. So we have actually one-to-one correspondence between the elements of Lie groupoid and something called germs. So if we consider a pseudogroup of diffeomorphisms that was generated by some vector field, then those are just local flow maps. As I stated before, a local flow map, the smallest family of local flow maps with restrictions. So we can consider some flow maps with respect to parameters that are well defined on those domains. Those are maps from this domain to the manifold. And if we can find such a neighborhood where they coincide, in which that point x of the manifold is in this neighborhood, then if they are equal in all those points in the neighborhood, then we say that those two flow maps, local flow maps, are equivalent at point x, because this is an equivalent relation, and such class of equivalence is referred to as germs. Sometimes, if this notation is confusing, I've encountered another one with like a square bracket and x rather than germ written directly. So actually, those germs can be composed. And in terms of if we because you can actually consider germs of an arbitrary function, those maps that I consider are flow maps. But the composition of the germs coincide with the composition law for the flow maps. So if we have a germ at if we want to compose two germs, so germ at y of some phi s and germ at x at phi t, we know that we can compose them only if that condition holds, and then the composed germ would be the germ at x of the phi at s plus t. So this condition must hold them, and this is the crucial condition for the composition of flows as well. So each germ can be identified with an arrow of a Lie groupoid, with the source of this arrow being just the point at which those germs are equivalent, and the target being this image of the flow map at this point. And we can see that the space of composable arrows is also defined with respect to that relation that has to be satisfied to be composed for them, and then the composition gives rise to a Lie groupoid element that actually is connected via this identification with the composed germs. Yeah, so this would be a connection between the pseudogroups of diffeomorphisms and Lie groupoids. And I think one can see that the Lie groupoid much better encodes like the locality of the problem. Right. So now, after this all being said, I will move on to Lie algebroids. And first, I would like to.
Małgorzata,
Yes.
just one question, because something is missing in what you have been doing. You have been checking the groupoid conditions, but what about the Lie part? I mean, differentiability and submersions and things like that. Have you checked it out? Or do you know how to check it out?
I did not check that actually. I thought.
Because,
Yeah,
for
this is
example,
a simplification. This is too big of a simplification, maybe.
this is just groupoid, you know, but for example, can you show the previous example, the action, the groupoid action example? Yeah, for a while. Okay. Yeah. Okay, this is the Lie groupoid, the structure map. This is the general stuff. Can you go to the Lie group action, the groupoid action groupoid?
Yes.
Yeah, this one. So here you have still to show a couple of things. The first thing is that the composition must be smooth, but this is quite obvious. The thing is, one of the things you have to request is that the source map and the target map, they have to be submersions, yeah? So this is what you have to prove still to show. But see that the S map is obviously it's subjective, yeah, and the tangent map, for example, for the identity or something like that, is going to be as surjection. So it is obvious that S is a submersion, yeah. And you can do something similar for T, yeah. You can work out the tangent map to T. Is going to go for the tangent to G times N to M, and it is also quite simple to see that it is going to be a subversion, because even not considering the part of the tangent map on the tangent to the Lie group G, the part on the M part is going to give you a summation. Yeah, the tangent map on the tangent space to S is already a summation, so it is going to be so. You see, you have to check these things, because in certain structures you can have action groupoids, but they don't need to be Lie action groupoid. Yeah, it depends on the action. In this case, there is a Lie group action, and you can see that it is also an active Lie groupoid. But there is a big difference, and in differential equations, we have a talk by Rui several months ago, yeah, and there were certain problems to see if a certain partial differential equations was related to an actual Lie groupoid or to a Lie groupoid or to a groupoid, yeah, integrated. So the difference is important. Okay.
Yeah, thank you for that. This was not explicitly stated and should be for it to be clear.
Yeah, indeed. At this time, it's just a comment, but if you try to extend this to partial differential equations, it's going to be a key. For this, there's no problem. For ordinary differential equations, it's quite easy. But then it becomes more complicated. These technical things, they have to be taken into account, okay?
Yeah,
but
sorry.
Everything fits.
Yeah, thank you. So now I will treat it as a true without the proof, but yes, it does indeed need one. Right, so I will just I think here, Lie algebroid. So Lie algebroid is an object on itself. I will later on also talk about the Lie algebroid of a Lie groupoid, but on itself, a Lie algebroid would be a triple of a vector bundle with the the bracket on the space of sections of that bundle, and with an anchor map that maps this is a vector bundle map from the bundle A to the tangent at the base space of this bundle, and also additionally the bracket on the space of sections must satisfy the Leibniz identity. So that a very primitive, very basic example is the tangent bundle, the algebroid. So we just treat the tangent map as also being the A bundle. We have the Lie bracket on the space of sections, which are here vector fields. The anchor map is from tangent bundle to tangent bundle, and it is just an identity. And the bracket, obviously, for the vector field satisfied the Leibniz identity. Okay, with the anchor because it's here just an identity of X. Right, but the Lie algebroid of a Lie groupoid is also triple, and here maybe before I state it, in this direction, I feel like this is from the definition, we have a Lie groupoid, we have a Lie algebroid of a Lie groupoid, but the inverse statement is non-trivial at all and requires a theorem that would be stated later. And there was a whole, as I think Professor Javier stated before, there was a whole brilliant talk of the author on the integrability of Lie algebroid. So that would be on that side. But with this remark, a Lie algebroid of a Lie groupoid would be a triple when this vector bundle that we have to have would be the kernel of the tangent to S map restricted to the unit elements with the base space, just the manifold M. So the manifold of objects. The anchor would be again the map between those bundles, but each element of the section. So here, this X denotes actually like the fibers of these bundles would be the tangent to the target map at the identity, and the bracket would be on the section. So the elements, the maps. The maps for the sections, which are the mappings between the tangent space of a Lie groupoid to a tangent space of a manifold M at identities.
Sorry, Małgorzata, I don't know if you said it before, but what is U? You write the vector bundle of the Lie algebroid is A is equal to U pull back. What is U?
The unit.
Yes, you're right. This is like the
unit, yeah? Okay,
unit, because
thank you.
you could, that's okay. Just to make it clear, because I said that the kernel of DS is restricted to the unit elements, and this is
Okay. Yes, I didn't notice. Thank you.
Sorry, that's okay. So just U or U on of M, for example. Yes. Right. So I will give again an example that would be relevant in the later example. So a Lie algebroid of a local action Lie groupoid. So we again consider action of a Lie group, but now it is locally defined. And we have a corresponding local action Lie groupoid, which is very similarly defined to the previous examples, but the space of arrows is the domain of this local action. So we have to keep track of this restriction. And the Lie...
Sorry,
yes?
before continuing, because it's something that maybe you will give still a talk in the seminar, something that we will ask you. You have U psi, yeah, in the domain. Could you say the properties of U psi? Which are the properties to say that this is a local Lie group action? Because there are several properties for it. Can you comment on it?
I think this might be for sure a local set of the product G and M.
It's a subset, yes, an open, but
open
which
subset.
properties? I will tell you, it's an open subset, yeah, and it must contain the element, the neutral element of G times M. Is the U psi contains all elements of the form EX. Yeah, E is the neutral element of G, and X is any element of M. Yeah, and well, it has to be an open container that you don't know what, but it's something like that. Yeah, this is something that
this is very basic. Sorry for that. Yes.
Never mind. It's just to recall you, okay? Because it's something that someone can ask you at a certain moment. It's something that it's convenient to know.
Yeah,
Okay,
I treat it as something very basic and then write it here, but I don't acknowledge that this identity element must be in the elements of this pairs. Yes.
Yeah.
So,
Okay.
thank you so much. So with the structure of a Lie groupoid, we, with respect to the definition before, can construct a Lie algebroid of this Lie groupoid. So the vector bundle would, as it is the kernel of the DS map, tangent to the source map at units. This is just the Lie algebroid. And so at each point, the fibers would be at each point we just have the Lie algebra space, and then the anchor would map elements of this algebra to the fundamental vector fields, and we have the Lie bracket on those vector fields here. So now I will move on to the example, which is the Riccati equation. This is a first order ordinary differential equation with time-dependent coefficient, and this is a Lie system. It has a corresponding time-dependent vector field of this form. And if we write the basis, which span the vector field, we obtain such algebra of vector fields, which we check their commutation relations. They actually satisfy the SL2R Lie algebra commutation relations. And if we integrate them, we obtain the corresponding flows, so the very basic translations and scaling symmetry, and some let's say, like action of the Mobius action, let's say. But they all can be rewritten in the form of the SL2R action. I will just in a second move on to that, but just notice that those two flows are well defined at each value of the T parameter. They can be obtained for any value of X on the manifold we are considering in. So those give rise to one parameter groups of diffeomorphisms. And this third flow, which is just generated by this X squared vector field that we have previously discussed as an example of the pseudogroup with the diffeomorphisms, is actually a local, with all the restrictions, actually is a local one parameter group of diffeomorphisms. And this is the restriction set. Obviously, there's singularity in the denominator. All right. So with that, since all of those flow maps can be actually, in general, rewritten in the form of the action of SL2R group as a general action of this form, we can match those coefficients to obtain those previous flows. With that restriction, we have a local action of SL2R on the real line where the elements which we are acting with are those SL2R matrices. And we have then a local action Lie groupoid. Again, the space of arrows is this domain of the action, and the structure maps are again as they were before. The objects are here, then the action is a target, unity acting with the unit matrix, and the identity with the inverse matrix on the transformed matrix, transformed point with the matrix, and then the multiplication is an action with has a corresponding arrow when we compose two matrices. So the composition of the flows here, the composition of the matrices that can be expressed by them, and the set of composable pairs, of course. So we see from the example of a Lie algebroid corresponding to this local action Lie groupoid that this would be a Lie algebroid that is an infinitesimal action of the Lie algebra of special linear group on the real line, with the anchor map mapping the algebra elements to the fundamental vector fields.
Małgorzata,
Yes.
here's a comment. Please recall that it is important, or it will be important at a certain moment, to differentiate between the action algebroid and the action Lie algebroid, between the action groupoid and the action Lie groupoid, because at certain times these words disappear. And as I said, in this case, it is easy to see what is going on, but with PDEs, it's not the case. It's something that it must be stressed. Okay.
Okay, thank you.
Yeah, you're welcome.
Okay. So the anchor map would map all those fundamental, all those elements of the basis of SL2R algebra into those fundamental vector fields, which satisfy the SL2R commutation relations. But this was an example on the real line. One could actually think of a generalization, how to, let's say, globalize it. I don't know if it's a good term, but what would be a global action corresponding object? So having this Riccati equation, we, rather than considering this SL2R Lie algebra action on the real line, we would switch to the projective real line. So include the infinity point into our consideration. Then there is no singularity in the denominator, because this is just one element of the manifold we're considering. And this Lie algebroid is integrable, and it's integrating into an action Lie groupoid with a corresponding action of SL2 R group on this real projective line, because this is the difference, the difference of the locality or globality with respect to the previous example. But the we could actually, I think, start with this Lie groupoid and then show that this is a Lie algebroid that arises from it. But as I said, there's an inverse question. So having a Lie algebroid, do we have a Lie groupoid? And this is not in one-to-one correspondence. There's not always, this is not always true. And the theorem I want to state is from, as was said before, the Marius Granik and Luis Roya Fernandez integrability theorem. There was a whole talk about that, so I'm not gonna outstand the author of the theorem. Let's just say that having a Lie algebroid, the object which determines the integrability of a Lie algebroid would be this monogrammy group, which is a subset of the center of isotropy Lie algebra, which is the kernel of the anchor map. So the condition that has to be satisfied in order to have in this Lie algebroid obtain a Lie groupoid is for every point x of the manifold for the monogramic group to be discrete. And then additionally, I think that the second is really the author's additional work improvement on this theorem. The family is locally uniformly discrete. And only then, if those conditions hold, we have a connected Lie groupoid integrating A, but up to an isomorphism. But I want to very stress it right now that as we had the algebroid of a Lie groupoid, we don't, as if we were to have an analog to the third Lie theorem that each Lie algebra has a Lie group. Here, this is not true for Lie groupoids and algebras.
Yes,
So,
Małgorzata, there was, if I may, as a comment, it's a fun thing, and it is interesting thing that it's very, it is known that every Lie algebra, finite dimensional Lie algebra is the Lie algebra of a simply connected Lie group. And in the theory of Lie algebroids, at the very beginning, it was to prove, of course, with a mistake, that every Lie algebroid could be integrated to Lie groupoid. It was a result I don't remember who that said that it is true, but at certain moment, someone found a counterexample from that cap the theorem, as it happens in many fields. And after several years trying to looking for solutions, Kreinik and Willoya found their theorem that was published in Annals of Mathematics. Is a very, very nice result. It's quite curious that at the very beginning it was thought that, every algebra can be integrated a Lie groupoid. They expected such a thing because they thought about the algebras of three-dimensional Lie groupoid.
yeah, thank you for that comment. Yes, I did not know that. So if we consider, so now let's state it again. I want to verify whether this theorem applies to finding out whether this Lie algebroid is integrable. So we have a Lie algebroid corresponding to the infinitesimal action of the SL2R on the projective real line right now. And the corresponding anchor map to the on the fibers to the tangent space at element x to the real projective line, and sorry, the foliation characteristic leaves are precisely the orbits of this SL2R action. And please note, or this is very much known, that the SL2R is transitive. So there is no other orbit. We have just one orbit, and the leaf of the characteristic foliation are just at each point are those whole spaces or real projective line. So isotropy Lie algebra, as it is the kernel of the anchor map, would be just the Lie algebra of the stabilizer of the point x. And since all those stabilizers are conjugate, the same, let's say, it is sufficient to calculate just one. And on the projective real line, we can calculate it for the infinity, one of the points, and the isotropy Lie algebra at that point would be of this kind, where those parameters are real. And to think of the monogramic group, we have to find the center, as it is the subset of the center, and we have to check whether elements of this Lie algebra commute with any other, so commute with the basis. And it is easy to verify that those indeed are commuting with any elements of the basis, provided that the elements of the matrix are zero. So we have just the trivial center of this Lie algebra. And as I said, these are all conjugate. So at each point X, those centers are actually 0. And the monogrammy group always is a subset of the center, hence this is just a trivial set, and hence the theorem assumptions are automatically satisfied. Okay, so with all that, I think with that review, we can see that the notions of Lie groupoids and algebroids are like a natural refinement of the pseudogroup viewpoint. Also, that there is a possible direction with the theorem of Krenk and Fernandez that the abstract integrability of Lie algebras are also a prominent further directions. So in physics, the applications, as Dr. Haver stated before, but also you can go to time-dependent systems, system reduction of differential equations, and the geometric theory of non-autonomous Lie systems, for example. And with many sources, I thank you for your attention and your time. This was a pleasure.
Thank you, Małgorzata. Thank you very much for your talk. So is there any question, remark, comment?
Yes, thank you for the nice talk. I have some questions, let's say. Well, the first one is when you have this case of a single vector field, we know that its flow gives a pseudogroup, right? And somehow this pseudogroup differentiates to shifts of Lie algebras, right? Given by the single vector field. And my question is, do you know if there is any characterization when a pseudogroup gives rise to a Lie algebra shift?
To Lie algebra, can you repeat the last, give rise to what?
Yeah, a shift of Lie algebras.
I don't know actually if I have an answer to your question. Like maybe you could reformulate it, or I really don't know, but
Yeah, I mean, the question is, well, in this case of a single vector field, we know that this pseudogroup somehow gives rise to a sheaf such that for every open subset, we have a Lie algebra sheaf such that in this open subset is just the restriction of the vector field. And my question is, do you know if there are any conditions for a given pseudogroup to give rise to a Lie algebra sheaf in a similar way?
no, sorry, I don't think I have any conditions of such. I don't really know. Sorry.
Okay, it was just a curiosity. Thank you.
Thank you. Sorry.
Oscar, I will tell you afterwards about that. Is there any other question, remark? No, yes, a quick one, okay? The example Małgorzata did at the very end is interesting, but the most interesting thing is that when the Lie algebra in many cases, when the Lie algebra is not complete, you can relate it still with a certain Lie groupoid by integrating it. In particular, this is interesting, for example, for Lie systems. There's something that sounded here we have been working on, because normally when you have a Lie system, it's related to a local Lie group, yeah, in a way that Lie algebra consists of the Lie system is the Lie algebra of infinitesimal generators of the Lie group. The nice thing is that in many cases, instead of working with the local Lie group related to it, you can work with the groupoid or the Lie groupoid related to this Lie algebra of vector fields. And in this case, the formalism that works locally for Lie systems can be extended, and many things, for example, in discrete methods for Lie systems can be generalized, and they don't need to be locally defined. I mean, it's quite useful for this theory in many cases, and it's a matter to introduce groupoids and Lie groupoids in the theory of Lie systems, and then to use reduction and use symplectic groupoids, Poisson groupoids, and things of the sort to study. So it's quite interesting. That's all. So thank you very much, Małgorzata, again for your talk. It's been a pleasure. And see you, everybody, next week. That next week we have, let me check for a moment, because next week we have Alberto Ibort from the University Carlos III de Madrid, and is the man. So see you next week. Thank you.
Thank you.